Okay, guys, the last part of this problem is really quite difficult. I just want to very quickly just take you through here and tell you that on the old AP exam, question number 1 was always an ice chart problem. The last part of this is very difficult. Okay, first thing, HCl is a strong acid. NH3 is a weak base. And ammonium chloride is neither an acid nor a base. This is a salt. All right, and each of the 3 beakers are 0.1 molar, and each of them have a volume of 25 milliliters. That's going to be important later on. First question, determine the pH of the solution in beaker 1. Justify your answer. What you need to know is that beaker 1 is a strong acid. We do not do ice charts for strong acids or strong bases. We do, there's lots of ways you can do it. I call it a BE chart. On the AP exam, you don't even have to like show work for this because HCl dissociates completely into H plus and Cl minus. And we can see that in the beginning, this was 0.1 molar. And then when it hits the water, this goes to completion. At the very end, this all goes away. And because this is a 1 to 1 to 1 mole ratio, these are both 0.1. And so what we know now is that the H plus concentration is 0.100 molar. And the question is, what was the pH? Well, pH is defined as the negative log of the hydrogen ion concentration. And so this is the negative log of 0.100 molar. Your calculator will say 1, but this has 3 sig figs, so you need to have 3 decimal, because once you take the negative log, only the numbers after this are considered significant. The number in front of the decimal point is coming from, because 0.100 times 10 to the 0.100 is 1.00 times 10 to the negative 1. So this has 3 sig figs. This has 3 sig figs, and this 1 here is coming from there. Just, it's a weird sig fig rule. Now, this beaker 2 is a weak base. Weak acids and weak bases, you always have to set up an ice chart. And so here's the deal. What is the KB expression? Remember, pure liquids and pure solids are not used in calculating equilibrium. So this ends up being NH4 plus times OH minus over NH3. That's it. And then calculate the OH minus in beaker 2. Well, this is interesting because what you have to do is you rewrite the equation, keeping in mind that liquids and solids don't, pure liquids and solids do not participate in equilibrium. All right, this is, I'm going to switch colors, but this is heavy-duty Bronsted-Lowry theory. This is the base, so this has to be the acid, and then this is the conjugate acid, so this has to be the base, the conjugate base. Not that you need to do that, but you can't do, NH3 doesn't have OH in it like strong bases do, like sodium hydroxide, which is Drano. You know, sodium hydroxide dissociates into sodium ions and hydroxide ions. This hydroxide comes from a chemical reaction with water. So moral of the story is weak bases are the toughest things to do ice charts on because you can't do Arrhenius theory. You have to do Bronsted-Lowry. So this is 0.1. This is 0. This is 0. This is not used. This goes down some amount, and this goes up the same amount because it's a 1 to 1 to 1 mole ratio. The reactant goes down, the product goes up. And then you add these together, so 0.1 plus negative x is 0.1 minus x, x, x. And then you use this row and this expression to calculate what x would be. I'm going to hit extend page. And what happens is KB was given to you as 1.8 times 10 to the negative 5. And then we have x times x over 0.1 minus x. I don't care how you do this. If you use solver, if you use quadratic formula, whatever X comes out to be, if you do this correctly, I like 0.0013 molar. Well, they didn't ask for X, they asked for hydroxide, but if you go up here and look, the hydroxide ion concentration is defined as X. So I would just go one step further on the AP exam. I would say, well, if X is 0.0013, then the hydroxide ion concentration is 0.0013 because you define that as X. All right, in beaker 3, we got this going on. Calculate Ka. This is interesting. One of the things, this is a tough equation, Ka times Kb equals Kw. That's an equation that you're supposed to know. I like it because one of the things from the reaction chapter, anytime an acid reacts with the base, you get a salt and water. But here's the deal. Ka is going to be Kw divided by Kb. Well, Kw is a constant. It's 1 exact times 10 to the negative 14. That's actually where we get the pH and the pOH. Always have to add 14. Kb was given to you as 1.8 times 10 to the negative 5. And if you do that in your calculator, you will get 5.9 times 10 to the negative 10th. Okay, now interesting, if you look, I'm going to go back to this equation over here. Let's go back. So what you're doing in the next part is they want you to take beaker 2 and beaker 3 and mix them together. And what happens is, if you come here, when you take this, I'm really going to switch to a weird color, purple. This is what's in beaker 1. Sorry, beaker 2. This is what's in beaker 3. I see a mistake here. This is Ca. And so basically what you have is you have a weak base and the conjugate acid of a weak base. And so what this equation is, very interestingly enough, is this ends up being a buffer system. Because what do you need to have a buffer system? A weak acid and the conjugate base of a weak acid, or a weak base and the conjugate acid of a weak base. And so I like this equation better. I do it differently than the scoring guide, but because NH3 is a base, and I'm always hammering on my students, bases, it's all about OH minus, and acids, it's all about H plus. This is equal to the pKb plus the log of the conjugate acid over the base. And I like this equation because if the base is down here, the base is down here. The equivalent equation that you would use if it was an acid, pH is equal to pKa, because acids are all about H plus the log of the conjugate base over the acid. But we're doing NH3 as a base. So the pOH, and remember, P just means take the negative log of the Kb value plus, and now this is the interesting thing. I don't really even have to stop and calculate this because I'm going to go back to the beginning. These are the same, because here's why. Let's go back to the beginning. Now, they're actually going to end up being half of this, but you have the concentrations are the same and the volumes are the same. And if you take two liquids that have the same concentration and the same volume and you mix them together and you would cut the concentration in half, because there'd be, so the concentration of NH3 would still be, you'd still have NH3, but then when you added this liquid in, it would make the volume twice as much. So it doesn't really matter that it's 0.0500. What really matters is that they're the same. And so what happens is, remember, you can see this Ca and B in this equation up here. This is the base, and this is the conjugate acid of a weak base. And so what happens is, these are the same, and any number divided by itself is 1. And then this is 0. So you end up with, because the log base 10 of 1 is 0, because the 10 to the 0 power is 1. You can just put it in your calculator. And so we get the negative log of 1.8 times 10 to the negative 5, because that was given to us. And then this ends up being 4.74. But the problem didn't ask for the pOH, it asked for the pH. Well, that's a very quick fix. So the pH is going to be 14 exact. That means 14.00000, infinitely many decimal places, minus 4.74. So this has infinitely many decimal places. This has 2. Best answer, 9.26. And then this is such a tough problem. I've practiced lots of different ways to teach this. The contents of beaker 1 are poured into the solution made in part C, which was beaker 2 and 3. The resulting solution is stirred. Assume that the volumes are additive. Resulting solution an effective buffer. That's the first question. Is the resulting solution an effective buffer? And the answer is no. Let me tell you why. This is the best way. Beaker 1 is HCl, which is a strong acid. And beaker 2 is NH3, which is a weak base. And beaker 3 is NH4Cl, which is a salt. And the interesting thing happens is when you put a weak base with the salt, they don't react. They're just both there. And that's why we could use the Henderson-Hasselbalch equation. But when you take beaker 1 and beaker 2 and mix them together, well, anytime you put an acid with a base, they're going to react. And then we have to do Henderson-Hasselbalch. We have to do Henderson-Hasselbalch is the buffer equation. We have to do Bronsted-Lowry theory, where this is the acid, and acids are proton donors, so it turns into Cl minus after it gives away its H. And bases are proton receivers, so NH3, when it picks up an extra H, turns into NH4. And so what happens is beaker 3 had NH4 to begin with. When you put beakers 1 and 2 together, this totally goes away and this totally goes away, and you make NH4. And so the first question is it an effective buffer? And the answer is no. And the reason is the strong acid completely reacts with the weak base. And remember, they have the exact same volume and the exact same concentration, so you're going to see that they run out at exactly the same time. You must have a weak base and the conjugate acid of a weak base to have a buffer. And we don't have the weak base. It's been completely consumed. Now this last question is crazy difficult. I'm going to do beaker 3 first. Beaker 3, nothing happens in beaker 3, because here's what makes this problem difficult. What was in beaker 3? NH4Cl minus, which dissociates into NH4 plus and Cl minus completely. This is a BE chart if you want to think about it this way. So this was 0.1 molar, 0.0. This goes completely away. This is 0.1 molar. This is 0.1 molar. And so, but I'm going to go to moles, because moles per liter times liter will always give you moles. And so what happens is you have 0.100 moles per liter times 0.0250 liters, which ends up being 0.0025 moles. So you got you have NH4 plus in beaker 3 is 0.0025 moles. Now, the interesting thing is beaker 1 and beaker 2, and when you think about it, there is no NH4 in beaker 1, and there is no NH4 in beaker 2, but yet, when you mix them together, this is a strong acid, this is a weak base. Acids always react with bases, and you will make it. And so what happens is the acid says, hey, I'm a proton donor. So when it gives away its hydrogen, it changes to Cl minus. And when NH4 takes NH3, receives the H, it turns into NH4. And so now we have to do an ICF chart. I'm not going to do the last part, as you'll see why in a minute. I have no idea why I picked that up. Okay, so what happens is, and this is mole, and this is mole, and this is mole. And so HCl is, this was 0.00250. This is 0.00250. Where am I getting that from? Because it's 0.1 moles per liter. And then it's times 0.025 liters. So the 0.1 moves it over a place. This is 0, this is 0. These are tied, so neither one of them are the limiting reactant. They are going to run out at exactly the same time. And the beauty is the 1 to 1 to 1 to 1, this is 0.00250, and this is 0.00250, and then this, and this, and then this, and then this. And now here's the interesting part. We got 0.00250 moles from beaker 3, because it was there to begin with. And then we got 0.00250 that wasn't there to begin with, but got made, and it's 1 to 1 to 1 mole ratio. That's what happens when you mix beaker 1 and beaker 2. And so you can see that this is 0.00500 moles total, but it asks for the concentration. Well, the crazy part is the volume is now 75 milliliters, because 25 mils from beaker 1 and 25 mils for beaker 2 and 25 mils for beaker 3, this ends up being 0.00500 moles over 0.0750 liters. And when you do that, you get 0.0667 molar. Let me just check that. 0.00500 plus 0.0750. Sorry, not plus, divided by. Pretty sure that's right. I've worked this problem a lot of times. Yeah, 0.066666. And that is it. And that last question is really, really